Okay, so in this little video we're going to be looking at the reactions of the amines. We're going to be looking at their basic properties and also how we prepare amines from other organic compounds. The major thing to remember with all amines is that they react in exactly the same way that ammonia does. So if ammonia will do a reaction, so will the amines. The amines might react a little bit faster or a little bit slower, but overall they'll do the same reactions that ammonia would do. So we're on page 5 of your notes and we're looking at the basic properties of the amines. So we haven't actually studied acids and bases yet. We're going to study those probably straight after Christmas. But you do have to have a basic understanding of what a base is. And a base we define as something which has the ability to accept a proton. And for a chemist, a proton is simply a hydrogen ion, a hydrogen positive ion. Now, the strength of the base is determined by the availability of the lone pair. So the better the lone pair is at accepting a proton, the stronger the base will be. The worse the lone pair is accepting a proton, the weaker the base will be. So we're going to be looking at the abilities of ammonia, butylamine and phenylamine to act as a base. And we're first going to react them with a very, very weak acid, water. Water is what we call amphoteric. In other words, it has both acidic and basic properties, and you'll study more about that later on. But if we take ammonia as our example, the lone pair on the nitrogen can take a hydrogen ion from the water molecule. So one of these hydrogens here attached originally to the oxygen detaches and attaches to that nitrogen. So we get NH4 positive and OH negative. And because we've done that, this is a basic solution because we've got OH negative ions present. We can do exactly the same thing with butylamine. We've just replaced, remember, one of those hydrogens with an R group. In this case, a butyl group. So we still have nitrogen, we still have our, this time, 2 hydrogens, and we have our carbon chain. So because it's but, we're going to have 4 carbons. So C4H9 plus our water goes to, and again, same idea, we've picked up another hydrogen. So we've now got an NH3 positive, we've still got the C4H9 plus OH negative. So you can see it's the same reaction that you get with ammonia. You just added a hydrogen ion on and gained a positive charge. Phenylamine, I'm going to actually draw this one. So it's what we call a benzene ring with an amine group on it. And again, we get the same reaction to occur. So again, this will grab a hydrogen, NH3 positive, and leave behind the OH negative. Now, this reaction here is not a very good reaction. It's very reversible. This reaction, again, is reversible, as is this one, but not to the same extent that these two are. Okay, so we'll talk about this. This is the strongest base, then this one, then this one. So the ability of these to act as bases is determined by the availability of that lone pair. So the more available that lone pair is, the more electron dense it is, the stronger a base it's going to be, because it needs to attract and hold on to those protons. Don't get this muddled up with electronegativity. This is nothing to do with electronegativity. It's the availability of the lone pair to attract and hold on to that proton. Now this goes back to something we looked at in the alkane and alkene packs specifically. And it's to do with the electron donating effect of methyl groups. So if you think about butylamine compared to ammonia. So I'm just going to use an R group to stand for the butyl bit. I've got nitrogens and my 2 hydrogens and my lone pair here. And I have ammonia. Very similar molecule. with a lone pair. Now these R groups, these methyl groups here, these alkyl groups, they are weakly electron donating, if you remember. So that's going to push electrons onto that nitrogen. And that's going to make that nitrogen's lone pair more available. Ammonia doesn't have any of those R groups pushing electrons onto the nitrogen, and therefore it doesn't increase the electron density of the lone pair. This R group does. So butylamine is a stronger base than ammonia because this R group can weakly donate electrons, increasing the electron density of this lone pair. Phenylamine, on the other hand, is a weaker base than ammonia. Again, if we have a look at the two molecules, we've got our phenylamine molecule, NH2, and our ammonia molecule. Again, we're interested in what's happening to that lone pair on the nitrogen. Again, there's nothing special about the ammonia molecule. There's nothing that's going to push electrons on or take electrons away. However, in this case, this ring here, this benzene ring, is electron withdrawing. So the electrons on the lone pair, or from the lone pair, go into the ring, away from the nitrogen. Now that reduces the availability of the lone pair. Because there's a good overlap between the lone pair on the nitrogen and the ring, those electrons are drawn into the ring, reducing the ability of that lone pair to accept a proton. So basically what you need to look at is, are there any groups which are pushing electrons onto the nitrogen? That will make it a stronger base. Are there any groups which are withdrawing electrons? And that would make it a weaker base. So anything with alkyl groups, or the more alkyl groups I've got on, the better. That's why dibutylamine is a stronger base than butylamine. Whereas phenylamine, because you've got this benzene group, which reduces the electron density of the nitrogen's lone pair because it sucks the electrons into the ring. It makes the ring more reactive, but it makes the lone pair on the nitrogen less reactive. Okay, so we're looking at the preparation of amines. The first thing we need to understand is that amines are good nucleophiles. So when we react a halogenylalkane with ammonia to make an amine, this is an example of a nucleophilic substitution reaction. The reason that ammonia can act as a nucleophile is because of the lone pair on the nitrogen. So the nitrogen has this lone pair of electrons, there they are, which you can use to make a dative covalent bond with something. And that's what makes something a nucleophile, an available lone pair of electrons. So if we take our halogenylalkane and we add excess concentrated ammonia dissolved in ethanol and we heat it in a sealed tube, we can get this particular reaction going on. So if we start with 1-chlorobutane as our example, so I have my 4 carbons, CH3, CH2, CH2, CH2 with a chloro group on the end of it, and I add excess ammonia, so there's excess of the NH3s, I can make a CH3, CH2, 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 NH2 on the end, and I get ammonium, NH4 chloride. If I do the same reaction but with limited ammonia, I can get the ammonia molecule here to do exactly the same, but it then kind of gets stuck at this butyl ammonium chloride stage. I can release the free amine by a secondary treatment with a different base, because all the excess ammonia is doing is removing that excess hydrogen ion. So I can use sodium hydroxide to do that instead. On the other hand, if I use excess chloromethane, in other words excess of my halogenylalkane, I can get successive substitution reactions to occur because I've got a lot of delta positive carbons to attack Remember that nitrogen, even though it's an amine, it's still available to attack delta positive areas. So I'll get a primary, then a secondary, a tertiary amine. I'll even get the salts where I use up the last of the lone pairs on the nitrogen. Now it's very difficult to separate these products even by fractional distillation because you've got a very similar boiling point here and therefore they're very difficult to separate. So the best way to produce these straight-chained amines, these are what we call alphatic amines, is heating your halogenalkane in a sealed tube with excess ammonia dissolved in ethanol. So this is a mechanism you've seen before in the halogenalkanes pack, but I'm just going to go over it again. So if I take 1 bromobutane and excess ammonia, this is a reaction I get. I'm going to use an R group just to stand for the most of the carbon chain. I have my carbon attached to my bromo group there. I've got a delta negative, delta positive. I have my ammonia and we have the lone pair on the ammonia that's going to basically push in to that carbon, pushing the electrons in that bond totally on to the bromine. And we get this salt as our intermediates. So I've now got the nitrogen which is joined onto the carbon, still got its 3 hydrogens attached, and it's now got a positive charge because the bromide has taken both of the electrons from the bond. One quick way to make sure you're on the right track is does it charge balance? So there's no charge here and the overall charge here again is 0. So this is where the excess ammonia comes into play. So I've still got lots of the ammonia knocking around the place. It can grab one of those hydrogens, again pushing the electrons back onto that nitrogen. And we get, if I can fit it on the page, we get our products. So we get our amine now, lost its positive charge because it's lost a hydrogen, or it's, so the electrons have gone back onto the nitrogen, and we get our ammonium, NH4 bromides, as our secondary product. The other way we can produce an amine is by the reduction of a nitrile, a C triple bond N. And we can use our standard reducing agents for this. We can use a hydrogen gas and a nickel catalyst, or we can use LiAlH4 in dry ether. That generally speaking followed by dilute acid to release the free amine. So we start with our butane nitrile. So there's the C triple bond N on the end. We're using hydrogen gas and a nickel catalyst, and we will make butyl amine there. We can also use reduction using LiAlH4 in dry ether. So here again we have our reducing agent, and again we can turn our butyl nitrile into our butyl amine. Okay, last but not least, we need to look at the preparation of phenylamine. So this is an amine where you have this benzene ring attached to it. And it is slightly different from the reactions of the alphatic group, so straight-chained groups. So we have to start with a compound called nitrobenzene. So this is a benzene ring here, and it has an NO2 group attached to it. The first step of this reaction involves tin, SN, and concentrated hydrochloric acid. Okay, so that's the reagent. That makes the salt. Once we've made the salt, and only once that salt has been produced, then in a second step we add sodium hydroxide. Now obviously we can't mix the sodium hydroxide and the conc HCl because you'll just get a neutralization reaction there. So you need to be very clear that this is a two-step reaction. And in fact, in most cases, in most exam questions, they'll just let you give tin and concentrated hydrochloric acid to produce the phenylamine. Now this is one of these annoying little reactions that you need to know. You don't need to know the mechanism, you just need to know the reagents and the conditions are what we call steam distillation. So steam distillation is our conditions for this reaction. Okay, so that just finishes this section of the notes looking at the amines. So we've looked at their reactions and we've looked at their preparation and their use as a nucleophile. In the last section of these notes, we're going to be looking at the amides, and that's going to be in the next video. So until then, take care, stay safe, bye-bye.